Hi everyone. So before I begin my talk, I have some disclaimers to make. So this talk is not about machine learning as a science, but it's actually about machine learning as concepts. So the concepts in there is actually not a single source of truth. It's from multiple sources on the internet. So don't take my word as the truth. And it's also not about the details of setting up a machine learning infrastructure, but it's more about the ideas of how we can implement these exciting machine learning ideas into our existing front-end development framework. So I'm basically going to talk about my expertise as a hobbyist. So everything here is a pet project. I never developed machine learning in my work, but it's just something that I'm very interested in. So before I go deep into the contents of my talk, I would like to make an analogy. So while I'm preparing this talk, by the way, I guess you all have seen Kill Bill, and if you haven't seen Volume 1 and Volume 2 together, I highly suggest you to go home and do that. Because actually how Tarantino first had Kill Bill, it was actually written as a complete Volume 1 and Volume 2 is one story, but then it turned out to be too long, and he had to cut it into half. So a lot of the things that I actually wanted to include in this talk about how web apps perform performance-wise with TensorFlow and so on is actually not going to be in this talk because it's just too much to include. So this talk is actually mostly focused on machine learning and basically the concepts that I think with the TensorFlow library that you would kind of need to know those fundamental concepts about what it actually does on the back before we dive into how to set it up into our existing development framework, which is what they call machine learning engineering. So a big part of it is about just how I wouldn't call it deep dive, skinny dipping into machine learning. So yeah, so it's actually just part one, the fundamentals. Okay, so actually I wanted to take some time to talk about the motivation behind machine learning. So as Reggie said earlier, I did an undergrad in engineering, so it's a combination of systems engineering and computer science. And I worked for 1 year in California as a software developer. But back then, software development was a very different world back then. And I find it to be very rigid. And I felt that, I should pursue a more creative career. So I actually went on to study architecture. So I was lucky because I went to architecture in an architectural school in the UK, which is famous for pioneering computational design. So meaning that they use a lot of scripts to generate design rather than talking about light and space and so on. So I was able to kind of exercise my background in programming to do a lot of architectural design. So this is actually an image from my master's thesis. So my master's thesis, I kind of wanted to show off in front of the architects, look, I can program. So I proposed a system to tackle the problem of pedestrian congestion by through image recognition from video to analyze how pedestrian flow within underground stations and use that data to feed back as an architectural design process to allow architects to design space that are more fluid and more adaptive to pedestrian traffic. And these are just some images that I used to used to analyze the space, and then I tried to construct network diagrams to analyze how much people will what the pedestrian traffic would be under different simulations and in order how it leads to architectural space. Okay, of course, all that stuff is bullshit. It's, that's the beauty of architecture because it's a very philosophical subject, so I don't need to actually make it work. I don't need to make a working prototype. I just need to make fancy diagrams to show, concepts. So, but then back in my mind, I was like, ooh, okay, if one day I can make it happen, that would be so cool. And if one day I can actually set up an image recognition system which can actually analyze real-time pedestrian traffic and input that into a subway system for it to continuously evolve and solve problems of pedestrian congestion, that would be amazing. But that's just a little dream of mine back then. And then I actually went on to become, my first job in the architectural industry is as a facade consultant. So as a facade consultant, it was a kind of in a spot where nowadays a lot of architects are doing something that, for example, like Zaha Hadid, she had, or Frank Gehry, they have a lot of very complex 3D geometry, which needs to be realized, as in like they need people who can panelize the crazy forms into actual panels. And those work usually get passed down to little minions like us, where like, we have to find out what's the best way to, panelize, as in like to cut off like surfaces so that, you can kind of like balance between aesthetic and construction costs. So again, I was able to kind of find this sweet spot where I can like utilize my programming background to think of like strategies and write scripts to like kind of automatically generate facade panel configurations that would kind of fit the geometry well while not sacrificing construction costs. So like back then, for example, this is one of the projects that I did for, during my my project in analyzing how to fit these kind of, the architect has a very interesting form where they want to like, have these aluminum glass panels and aluminum panels to fit this like crazy double curved surface. And I kind of like developed some algorithm to try to like, break it down. I think like slicing it like this would work. And I would develop all these like rule base for it. And then I'll put all the data. Okay, the main idea again for me to show these diagrams is all these are kind of like fancy diagrams to convince our clients that like, hey, we know what we are doing. But to be honest, I have no idea what I'm doing. I just like think that, this way would be like the best way to do it, and the numbers look like okay, and the price is not over the budget, then, can call it a day. And so, but then back in my mind, I was always wondering like, oh, what if I know machine learning? Then I can kind of like, teach, write a script that like instead of just me imposing all these rules on it, it can like kind of learn from all the previous projects with the budget and with, in terms of like, aesthetic to have this script to learn about how the best way to panelize this service. So that's another dream of mine in my mind, and so this is actually one of the final projects that I did before I made my switch back into software development. So it's a V&A museum in Dundee. So the photos, by the way, you guys, it's opening in September. It's an amazing building, so you guys should definitely check it out. And so one of my role in this project. It's for this architect called Kengo Kuma. This project is it was extremely over budget because all the panels, all these like what they call like precast concrete pieces are they all like custom made to fit this again like crazy complex surface. And so we had to actually kind of find ways to minimize the cost, which is to kind of group them into families. And with that, like, I went in to do a lot of analysis, and within like the normal, like if it's like a straight plank, then it's okay. But with the corners, like the corners are the really tricky bits, which I try to write a script that tries to apply a lot of the rules that's set up by the subcontractor with costs and so on. And in the end, like, there's just too many rules to govern, like, how to design a corner that looks nice at the same time, not sacrificing costs. And in the end, what I ended up doing was I manually actually went on to model each corner piece. So if you see each of these corners, it's actually like, designed by sweat and tears and many overnights. So yeah, but at the same time, it would be so great if I know machine learning that I can design a script to do that, to learn about like, aesthetics, for the script to learn about how to do it and so on. So before we dive into machine learning, the first question actually we need to ask ourselves is, do we really need machine learning? So meaning, for example, like if I want to design a robot that would like, help everyone in the office like do a coffee run, then like, if the robot actually like, goes to the same coffee shop to fetch the same coffee and then comes back, then you pretty much don't need a machine learning script if it does the same, if it can be defined by very simple rule sets. However, if you want a robot that you don't need to interact with, but it will just automatically, a hot day, bring you like a cool frappuccino, then for the robot to be able to learn what you want to do, then what you want without you telling it to do so, then you kind of need prediction. So in other words, like if you're Jin Yang, the Octopus app, you don't need machine learning, but you're making the hot dog and not hot dog app, then you need machine learning. Yeah. So the best solution is it's always easier to calculate than to predict. But let's say you decided, okay, I want to make a hot dog app, hot dog apps, then you will have to look into machine learning. So before we look into your problem, the first thing you really have to define is whether it's a classification problem or a regression problem. Meaning that whether it's something that whether it's spam or not spam, whether it's cat or dog, or whether you want to calculate meaningful predictive values like housing prices. And then in machine learning, there's a terminology called label. So label is meaning that, for example, in the case of the spam, then the act whether it's spam or not spam is called label. Versus you have all these features that which are pretty much like input data that you analyze. For example, your sender, at what time it was sent, your content of the email, and also certain keywords. Like if you have a keyword that says sexy babe, then maybe it's spam. Yeah. So the fundamental goal of machine learning is to minimize errors. So it's not. So it's different from AI in the fact that AI it's a branch of AI, but it takes a very different approach where it tries to learn and and the approach to learn is to minimize errors that they make. So this is a very typical iterative process of how a machine learns. So you would actually input a series of feature data into your model, and then your model will try to make a wild guess, and then they will compare that wild guess with your label, which is so you input a series of sender feature data, and then actually it turns out that it's not spam. But then they will compare the loss, and then they will, after they compute the loss, and then they will input that back into the system to further for the model to iterate until it reaches the optimal point where it has the least loss. So for example, in this case, so loss is a very important thing within the machine learning training process. There's many loss functions out there. This is a very typical example of a mean squared error where you take all your data and then you take out all the differences between your actual result and your prediction, and you squared it and then divide it by amount of data. So this works if you don't have that much data. But then what if you have tens and thousands of data? Then calculating the mean squared error is actually not a very optimal way to do it. And then it comes with the stochastic gradient descent. So gradient descent is a type of a method to find the minimum point, meaning that, for example, if we plot the loss against the value of weight, so this graph is actually an instance of your model param, meaning that this is actually how your model is performing at a certain period of time. And so the model will start with a point, meaning a starting point is just any wild guess that they go in, and then they will start doing the prediction, and then they will calculate the loss, and then they realize, oh, I have this much of loss. So it will on the graph this graph will help them determine the next point to enter until it reaches the bottom of the curve. So there is something within this concept that with the learning rate, as in if you have a learning rate that's too small, it would just take forever for the model to learn to reach the minimum optimal point. Versus if you set learning rate that is too high, then it will just what they call like, it will overshoot the minimum point, meaning it will never reach the optimal state. So determining the learning rate is actually a very important part of machine learning. But to be honest, I still have no idea what's the best way to determine the learning curve, but as long as like sometimes it reaches a pretty good prediction model, then yeah. So just don't set it too high or too low. And so with this, so with this, this 2D graph of SGD is just only applies to linear regression. But in most cases, like when let's say if we want to run like an image recognition model, which is you need to use the CNN, the convolutional neural network, or just normal neural network, then it will actually be kind of like, it will be a multi-dimensional model, meaning that, and it will normally shape like a crate, meaning that there are several like optimal minimum points. And so within the training process, so it's pretty much like, the model will kind of oscillate. It could potentially oscillate between the different minimum points of your model. So this is how, like visually, like what your model would be doing during the training process. Next, we are actually going to look into the TensorFlow.js library. So there are many libraries out there, like many Python libraries out there. So I'm particularly focusing on TensorFlow.js because it's in JavaScript, meaning that we can actually easily integrate this into our existing development framework. And you can actually run your training and prediction models in the browser. So that's actually something very exciting. And one important thing about TensorFlow.js is it used to be called deeplearn.js, and before it was acquired by Google, and it got integrated into tensorflow.js. So a lot of the tensorflow.js library is mainly used to do neural network models. So that's why today we are just mainly looking into neural network. So here I'm using an example that's actually from the TensorFlow.js GitHub repo, and I highly recommend all of you to, if you're interested in this, to go and like download the repo and go through the code. Today I don't have too much time, so I'm not going to go through too much of the code in detail. But so it's just a very classical project where they will input a bunch of like images with handwritten letters on it, and then the model will, like, after training against all the handwritten letters with labels, then they will take in a bunch of images, and then they will use that to predict the handwriting of a series of new incoming images. And then it also shows like how it's plotting the loss. So the diagram here is pretty much like showing the model, how it, like during the training process, how it reduces the loss and at the same time increasing the accuracy. So this image is taken from the TensorFlow Playground, which is pretty much like the visual presentation of the TensorFlow workflow. So to be honest, TensorFlow, when you get the gist of it, is very straightforward. It's pretty much just follow these 4 steps. So you need to prepare your data, you need to build your model, you need to set these parameters to train your model, and with your model who is learned, then you can use that model to use prediction for future items that are not labeled. So we're going to go through all the concepts one by one. So first, we're going to go through data. So there's 2 types of data. So there's one type of data that we use for training, and one type of data that you use for prediction. So meaning that training data, for example, labeled examples, the example update is the data we use for training. So the training data, meaning that you have, for example, in the case of like house prices, so you have a series of data where you have the median age, the total rooms and bedrooms, and then you have the price associated with it. So you input that data into your model for training, and with your trained model, then you can use that. You can input a new set of data into it, which is the future data, and you use that for prediction. So one important thing that you need to look into about data is, so normally let's say you get an object data from your web app, and then the data is in all sorts of format, like it can be in numbers, it can be in strings, but model doesn't, you can't just dump that into your model. You have to convert that into factors and what they call feature factors. And so basically the conversion of your data from JSON data into your feature data is an art itself, and what they call feature engineering. So, for example, if you have number of rooms, you can just directly translate that into if it's an integer, you can just directly translate that into 6 in your feature factor. But most often, your data is in the form of strings. Oops, sorry. And then in strings, you basically need to convert that into a vector. For example, in this case, you have a street name. So how would you convert a street name into a vector? And then that's actually something that, if you are working in an actual commercial machine learning actual development team, then that would normally be determined by the machine learning scientists, where they decide okay, this type of input, this type of value will be assigned a binary value of 1, and let's say Main Street is a binary value of 1, and then other not so important or small streets, then it's a factor of 0. So this process of converting string data into vectors is called one-hot encoding. And if you're interested, you can read up on that. That's itself has a lot of scientific theories behind. And one important way, or what I find the TensorFlow playground is so nice, is that it allows you to visualize your data. So this is a classification model where, so let's say, let's say when you plot feature 1 against feature 2, let's say if you plot the sender against the keyword, then all the different colors on this diagram represents whether, let's say blue represents spam, red, orange represents not spam. So from this visualization, how can you tell about this model? This model is doing really shit. Look at it. Most of the blue dots is in the orange area, and most of the orange dots in the blue area. So at this time, your model is not trained yet. So and then you just need to need to tweak your model, or you need to maybe you need to tweak the learning weight and so on. So this snapshot instance to visualize your data is actually very helpful. And there's actually an important concept of training set against test set. So training set, it's obvious, you use that data to train your model, but what would you imagine a test set would be? So when you have a model, you don't, of course, you can take a snapshot and kind of see how well it's doing. But one important way to verify that your model is working well is once you've trained your model with your training data, you test your model with your test set. Meaning that you take out the data and you use the model, and then you run your test set against the model to see how well it's predicting. And that's, so test set is very important within the machine learning training process to verify how well your model is doing in its prediction. So, in the sense that, in this case, TensorFlow, before you construct your model, you need to, usually most people would do a data.js class to kind of define and prepare your data. And it's just, to be honest, it's just mostly these 4 simple steps. You need to just load your data, you need to shuffle your data because you don't want your data to be in a certain order so that the model would be biased. And you need to split your data into training batches and test batches. And then you also need to define your functions for you to fetch the data so that later on you can call those functions to load your training sets and test it. You don't dump all your data into your model all at once. You would actually, after running against, you call them in batches and you train your model against the batches. Okay, so by the way, I bought a Mac just for this. For this animation. And I'm not going to go through the code in detail because, code is just code. But pretty much okay, here, so you would actually use a promise to load your image. And in this case, since it's image recognition case, so you need to kind of convert your image data from pixels into a vector. And then you also fetch another you also fetch your labels. By the way, all these images is actually from a Google API. They have this exercise where they have already loaded a series of images, handwritten images for you. So you just need to call it from an API. And then of course, like, you would call another promise to load all your image and the label data. And then you need to like shuffle your data, and then you need to split your data into training set and test sets. And then you call a function to you construct this function to load your next training batch and your next test batch, and then you have like your next batch of data will pretty much we'll call both test batch and the training batch to load the data into the model. Okay, so the next fundamental concept is about the model itself. So the model. So we use a neural network. So it's pretty much an analogy, but back then the scientists looked into like, a human brain, because it's the most intelligent thing on earth, and how the human brain processes information. So a neuron pretty much takes in external information once you pass in a neuron, and then it will spit out a new series of processed information that gets passed on through different layers, and it will become like, processed information, or what they call like, and that is the learning process. So in a neural network, each neuron is pretty much like they take in all your feature data. They apply the weight and a bias. So the W is the weight and the bias to it. But that formula itself is pretty much linear regression. What you see, but normally in the real world, you will need an activation function because, for example, I will explain a little bit more about what activation function does, but anyway, yeah, it will apply an activation function and do an output. So this is, pretty much what a neuron applies, the weight and the input, and with the input and the bias, and that's linear regression. And then you apply an activation function to it, and that's the non-linear transformation, and that's most of the use cases of machine learning. And there's many different types of well, not many, but like most 3 common types of activation functions. So what is an activation function? To be honest, it's, even for me, I don't know even whether I've grasped the concept clear enough, but it's pretty much in neurons. So, they will have this idea whether they would fire the information or not fire the information. So in the sense that it's whether the name activation comes from whether the information is activated or not activated. So so that's in a very simple classification case where the information, whether it's spam, not spam. So but in most cases, you would like, let's say, predict a number, and you want to predict the probability of that number. So that would be a plot. Like, so there is the sigmoid and tan, which they'll pretty much take your input number, and then they will shrink it within all your data into like the scale of 0 to 1, or in the case of tan, which is -1 to 1. And then they would output the, kind of like processed information in the form as a probability to move on to the next stage. And ReLU is actually a very common case of activation function that's mostly used by most machine learning scientists nowadays. And ReLU pretty much like anything that's not activated, they would just give a probability of 0, and then it will automatically scale up. So if you have a larger number, it would just output a larger number. And to be honest, I don't have the scientific answer as to why ReLU is the best. Oops, sorry. But this is from the docs of TensorFlow, and you can see like ReLU is pretty much like the most commonly used method as an activation function. And for most of the tutorials that I see online, they use ReLU. And this is like a brief anatomy of a neural network, meaning that you have an input layer, which is all your feature data. You pass them through a series of what they call like hidden layers to learn your output layer. So question. Does it mean that if we put more layers in it, does it mean that you would have a more accurate model? So considering this case, so we have a series of data. There's not a lot of data sets, but then let's say if you apply a lot of layers, so it's really fitted. So if you can see in this model, it can clearly identify the orange from the blue, but doesn't mean it's a good model. no, it actually is a really bad model as well, because it fits really badly for incoming data. As in when you put new data to make predictions, it wasn't able to fit to this other new set of data. As in, it's too fitted for one certain set of data, and meaning that basically in machine learning, you cannot have 100% accuracy. If it's 100%, then there's something wrong with the model. And so that's why you only want to apply an optimal number of layers to your model. So back to our example, so it's the image recognition problem. So most people, basically, everyone uses the convolutional network model to do image recognition and image analysis. So it will use the layer is called convolutional layer, and it uses the value activation function. And it will also pass through another layer which is what they call max pooling. And I'm going to explain that more in detail in a second within the code. So, so in your model, so you first, of course, you input all the data functions that you defined earlier, and then you would call model basically construct a model with tf.sequential. Pretty much, it's a chaining API that lets you chain with more layers later on in the code. And then you would add your first layer, which is the Convo 2D layer, and it's from the TensorFlow.js library. And with the first layer, you have to define the input shape, which it's 28 pixels by 28 pixels for each image, and 1 because it's a 2D image. And then you have to also set activation function, which is value, and so on. And then you also add a max pooling layer. Okay, so max pooling. So what is max pooling? So max pooling is pretty much like the of course, you cannot analyze every pixel. So max pooling, so for all the information that gets past one layer, so all the processed information, all the pixels, they will assign weights to each pixel. And within that, they would use max pooling, as in they would take out a region and find the maximum number within that region for it to be passed on to the next layer. And so within that, in this example, we call another convolutional 2D layer, and you also do max pooling after that layer to, so it will, the image will be scaled down, with max pooling scaled down 2 times. And then, because this is a classification example, so with classification, you would add, before you would, the last layer is pretty much the classification layer where it determines whether it's a 1 or a 2 or a 3 or 4, and then which is pretty much what this last layer, this dense layer does. Okay, so the last part is about training. And with training, I'm not going to go too deep into training because training itself has a lot of theories, and this is pretty much what it does on the back with training is they need to, so you pass in your data to it, and then once the model makes a prediction, goes through the neural network, and then it will go through exactly like what it says here. You will calculate the loss function, and it will actually go back to after obtaining the loss. It will actually do what they call a back propagate execution, where they would actually go back to each step of the model and then reassign the weights for each layer within your neural network. I'm not going to go too deep into the detail of it here, but then because you don't need to set any settings for the back propagate method in TensorFlow. But if you're interested in that topic, I highly recommend you to go and read up on that. It's very interesting. So to train a model, you need to define your optimizer, pretty much the method how you define your loss function. And here, the loss, we use categorical cross entropy because it's a classification case. And again, under which case, which loss function to use is the best, it's something that's really worth reading up on. And you also need to define your evaluation metric, and all these 3 together will combine to compile your model in the training process. And then you define your training loop. So again, here I might skip through the code because I'm kind of running out of time, and there's a much more interesting part later. So here you determine your batch sizes because as I mentioned earlier, you don't dump all your data into your model at once, and you define your batch sizes and how much data you feed in each time. And then you start to, okay, so this is your train function where, you basically, this is the part where you define your iterative process to train your model. Yeah. And then, yes, and then, oops, and then, sorry. Okay, so pretty much the last slide was just to show, like, there's a part where, you show all your prediction data. Okay, so with all those three concepts, like the data, the data preparation, the model construction, and then defining a training loop, and putting it all together is just 3 simple steps. You just load your data, you train your data, and then you show your predictions. It's that simple. And so here I have like basically the video of actually how it works and what it actually does. Everything here is done in browser. So now it's actually loading all the data and actually starting to train the model. And it's exactly, you see here, like, the model is going through this training process where it's like, you just imagine like that crate where it's trying to find the lowest point. It's basically doing that when it's like plotting that data. And you see that accuracy goes up as loss decreases, and then after that, they are able to make all the prediction of this new set of incoming images. All this is done on the browser. So, it's pretty exciting, the TensorFlow library. And okay, so after all the fundamental concepts, like, okay, so now we know what the code does. So now we can, get back to, the most important part as in machine learning engineering, because, we are all engineers. We want to create. We're not scientists. So the files I showed you just then is just the data.js and the model.js file. It's only like a tiny part of what we call like, machine learning engineering. And all these other parts is pretty much like what we as software developer does best. We need to set up files that would do the data collection, the data verification, and monitoring of your data and so on. And I have to say I'm biased and I love React. So the examples that I'm going to use here will be based on React. And so yeah, meaning all this things that you have to develop around this machine learning feature, it's all actually can be all fitted into your React development environment. And for example, like I can already imagine using Redux to fire actions to extract your features and verify your data, or maybe you can use GraphQL to as another type of architecture to monitor your data. So this is just some inspirations I'm throwing out there. So with machine learning, one very important part that you have to look into is whether you are designing a static system or a dynamic system. So meaning that, like, as the title infers, static system is pretty much like, you train on an existing data and use that same data. You don't update your training model to make future predictions. For example, if you want to predict how many people are going to the beach today in Barcelona, you take the data from like, last year, from like, September to August, and then you train that model and use that for all future predictions. With a dynamic system, your model will, other than like, using your model to predict, a trained model will continuously train and update according to new incoming data. So in front-end development terms, meaning that like a static system, you can actually run all your trained model on your client side because there's much less latency as compared to a dynamic system, because your model is constantly like training as well as doing training and prediction. So it's best to be run on the server side. So okay, so as an example, I have an app idea, which is combining Tinder and Twitter, as in like, okay, do you guys use Tinder? If you're single, I highly recommend you to use it. You make a lot of friends from there. And so my idea is to combine the two, so you can like, it has a swiping interface to learn your preference about different tweets, and then it will create, the tweets that you like. So, let's say whether the difference is Donald Trump or emo Trump, it will create different data for you according to your preference. The first architecture that I can think of is, if it's like just a client-side system. By the way, it can definitely use with dynamic systems as well, but it's just something that I'm throwing out as an example is using React Redux and TensorFlow to design this static system. So, you have a swipe component, we will first call, the Twitter API for, according to a search keyword to show you tweets. Let's say if you want to search about pizza, and it will show you all relevant tweets according to pizza, and you indicate whether you like and not like. Well, it will, the Redux store will fire, reducers will fire all this, data for your model to train. And then later on, you will use the same model. It wouldn't update because the latency is just too high on the browser side to continuously train and predict. And then you just, and later on after they've trained and learned your preference, then it will just show a tweet display component to constantly update your tweets. So the other, to construct like a dynamic system, one idea I have is to use GraphQL. But again, I'm biased because I'm a huge fan of GraphQL. It's a very, very clean and simple way to approach front-end development. And with GraphQL, just a slight background that they have a query. It's basically a layer between your web app and your API. And it allows you to do things such as you can query your data, you can subscribe, and you can mutate your data from the client side to your event store. So in the dynamic system case, you can have your component to first again, learn your tweets, and all this prediction is done on the cloud. So it will have the GraphQL event store will fire all this training events to the cloud. And then later on, with your tweet display, then it can still continuously, accept feedback from the user to, and through GraphQL subscribe to continuously subscribe to this like and not like event for the user to, for the model to continuously, run the training model and prediction. Okay, so this is pretty much what I have, and I would love to end with this slide. This is my favorite scene from the movie when Uma Thurman is going out to get her revenge. And pretty much now, once you know the basics, you can just go out and create all these amazing features and things that you can do with machine learning. And this is the quote that I would love to end with: is we are not scientists, but it doesn't mean that we cannot do machine learning. And we should just do machine learning like the great engineer you are, but not like the machine learning expert that you aren't. And so that's pretty much it. And for next year, I'm also planning to continue this hobby of mine. And then hopefully in the part 2 of the presentation, I can go and talk into more of the difference between those two different architecture between the static and the dynamic system and how it performs and so on. So. Yeah, that's pretty much it. Thank you very much for your time. Yeah.